Hey there, geometry gurus. Mr. Stewart here, ready to start Unit 4. Unit 4, dealing with dilations. Just like the diagram, dilation is when you go to the eye doctor and they dilate your pupils, which means they make them bigger so they can see into your eyes better. But dilation doesn't always have to make things bigger. It could make things bigger or smaller. This is going to be the fourth out of the 4 transformations that we do this year. We've already done reflection, rotation, and translation. Dilation is the 4th one. So, our opening exercise. Which of the images below appears to be a well-scaled image of the original? A well-scaled image. Kind of like snapping a picture on your phone. You zoom in with your 2 fingers, zoom out with your 2 fingers, and the picture looks the same, just bigger or smaller. A well-scaled image will look exactly the same as the original, just different sizes. And we're going to be focusing on how and why that happens. So obviously the third bicycle looks like the original bicycle, just maybe a slightly different size. Now in geometry, when we create a well-scaled image, we are performing a dilation. A dilation is the 4th and final transformation that we will construct. I'm going to show you how to do the construction of a dilation today, which means you will need a compass and a straight edge. If you do not have a compass and a straight edge, you can continue to watch the video, but until you do have a compass and straight edge, you obviously won't be able to do and practice the dilation constructions. So the specifics about dilations. The notation for dilation, and it's dilation, not dilation. The A is after the L. You dial a phone, you dilate an object. So anyways, the notation for dilation is a capital D with O, which represents our center of dilation, and the R is the scale factor. Now the scale factor is the constant of dilation by which all side lengths are multiplied. So I'll slow down so you can fill this in a little bit. But what a dilation does, it multiplies each side length by the same number, so all sides either increase or decrease by the same scale factor. When you swipe your fingers across your screen to zoom in or zoom out, the program is built and designed to shrink or enlarge everything in the same ratio so that the picture does not look distorted. That ratio is called our scale factor. A dilation is a transformational rule that moves a point a specific distance along a ray that originates from the center of dilation. If your scale factor is bigger than 1, then your dilation pushes the point away from the center of dilation, which means your object gets larger. Now that should kind of make sense to you. If your scale factor is bigger than 1, then your shape is going to get larger. If your scale factor is between 0 and 1, the dilation pulls the point back towards the center of dilation, which means your shape gets smaller. If your dilation is negative, that means the dilation will move the point in the opposite direction of the pre-image. So it actually moves away from the pre-image. It can be away from the pre-image and smaller if it's between 0 and -1, or away from the pre-image and larger if it's less than -1. If your scale factor is exactly 1, then nothing changes because you're multiplying all the side lengths times the number 1. Size stays the same. All right, so we're going to do a dilation construction. So go get your compass and straight edge. We're going to dilate segment AC by a scale factor of 3, centered at point C. So the first thing I want to practice is writing the proper notation for this dilation. Remember, it starts with a capital D. We need the center of dilation, and we need the scale factor. So our proper notation is a capital D for dilation, C is our center of dilation, and then 3 is our scale factor. So let's do the dilation. What you're going to do first is take your straight edge, line it up with point C and vertex A, and we are going to just draw a segment nice and long. Then I'm going to use my compass, move this out of the way, and we are doing a dilation of 3. So that means I'm going to measure the distance from the center of dilation to the point I am dilating, in this case point A. I'm going to measure that distance with my compass. That is considered 1. I want to do a dilated distance of 3. So that means I'm going to take the distance from C to A that we just measured and mark it off 3 times. That distance that you see on the screen right now is considered 1. Now I'm going to slide my needle up to that first mark and mark it again. That's 2. One more time. That's 3. There's my new A prime. A prime. Now I follow the same steps for point B. Put my straight edge on C. Line it up with vertex B. Draw a line nice and long. I'm going to measure C to B this time and mark off 3 of those lengths. From C to B does count as 1. So there's 1. Keeping the compass the same size. There's 2. And 1 more. There's 3. There is B prime. Now I can take my straight edge, connect A prime to B prime. And I'll have my segments. There's my dilated segment that is now 3 times larger than the original AB. So now what I want you to do, pause the video, use a ruler to measure to the nearest tenth of a centimeter, and find each of the following lengths that are listed on your paper. So use your ruler. I'm asking you to do it in centimeters, so make sure you're using the correct side of your ruler and measure each of the given segments. When you're done, come back to the video. So what we should have seen from your measurements, and yours are might be a little bit different from mine, which is okay. But what we notice, or what you may notice, is it's the same ratio, which is exactly what should happen because the dilation takes all your lengths, multiplies it by the same number to get to the new lengths. So if I take the new length and divided by the original length, that's the image divided by the pre-image. So the image length divided by the pre-image length, we have 9 divided by 3 for CA and CA prime, which reduces down to 3. If I look at CB, it's 12 divided by 4, which also reduces to 3. And same thing with AB, A prime, B prime. So what we're seeing here in our diagram is that it doesn't matter if we measure or look at from C to A and then C to A prime to get our scale factor. We could look at C to B and then C to B prime, use those values to get our scale factor. We could also do AB to A prime, B prime to get our scale factor, because all those segments increased by the same scale factor. And they all showed a scale factor of 3, which is what it was supposed to be. That means we did our construction correctly. What else do we notice about this diagram here? And A, B are pre-image, and A prime, B prime, the image. Well, they are parallel. So a dilation produces a figure that is different size, either bigger or smaller, but all the corresponding sides are parallel from pre-image to image. All right, we're going to do another dilation by a scale factor of 2 centered at O. So I want you to write the proper notation for this dilation. Centered at O, scale factor of 2. And now what I want you to do is pause the video, do the construction, and then come back and we'll continue on with the notes. So you should be doing this construction on your own, but what you're going to do is line up your straight edge and connect O to C, nice and long, O to A, nice and long, O to B, nice and long. Then you're going to measure with your compass the distance from O to C, and then you're going to mark that distance twice, because our scale factor is going to be 2. That first mark counts as 1. Oh, this is so much easier on paper. So hopefully your construction looks similar to mine. We have A prime, B prime, C prime dilated with a scale factor of 2. Based on the example that we did, we know that each line segment is going to be double the length of the pre-image because our scale factor was 2, so everything, all the lengths got 2 times larger. So if the original perimeter was 9.2 centimeters, we take that original perimeter, double it, and then we get the new perimeter. Very simple. If all the side lengths were doubled, then the perimeter was also doubled. Now, the ratio of line segments that represents the scale factor, it can be any pair of corresponding lengths, but you have to write it as the image length divided by the pre-image length. So we can actually use the sides of the triangle and do image divided by pre-image. A prime, B prime divided by AB. We could do B prime, C prime divided by BC, or A prime, C prime divided by AC. Always image divided by pre-image. We could also, as we discussed in the previous example, measure the lengths from the center of dilation to each vertex of the triangle. So OA prime to OA, or OB prime to OB, or OC prime to OC. Any of those comparisons will lead to the same scale factor of 2. All those ratios would simplify down. If we had a ruler and we measured all those segments, each one of those would simplify down and give me a ratio of 2, or a scale factor of 2. Now what about the angle measures? Angle measures, do they double as well? Well, let's do this. I have the ability here on my computer to trace over this triangle that we just made, and then I can trace over the original triangle that was given to us. I guess we'll do yellow. And let's see what happens with the angle measures. So I can drag this one on top of that one. Looks like the angle measures match up, even with my rough sketch. Looks like the angle measures all stayed the same. So the side lengths changed, but you can see I can put one angle on top of the other, and it's just a hand sketch, but you can see these are going to be the same size angles. So our side lengths changed, but the angles remain the same. So if we had a protractor and could measure the angles, we would see that all the angles stay the same. So I got these measurements by using a protractor while you were gone. All right, so now how do I do a dilation that is a half? Well, it's the same way you would do a perpendicular bisector construction. You would use the perpendicular bisector construction to find the midpoint. So if you want to do a scale factor of 1/2, then you just need to do half the distance from the center of dilation to the point that you're dilating. And if we're doing a scale factor of 1/2, I just need to go halfway there. Using a ruler? No. We don't use rulers to find the middle. We use compass and straight edge. So I connect O to C, and I'm going to bisect that segment to get the midpoint. Then I'm going to connect O to A and bisect that segment to get another midpoint. And then same thing with O to B, bisect that to get a third midpoint. The three midpoints would be the three vertices of the triangle that is now dilated by a scale factor of 1/2. So take some time, pause the video, and bisect each one of those segments, OC, OA, and OB. That way you can find the midpoints, which would be the three vertices of the new dilated triangle that represents half the size of the original. So pause the video, do the construction, then come back. Welcome back, and as you notice, these can get pretty cumbersome and pretty cluttered with a lot of lines and arcs and segments drawn, so you need to be careful and pay attention to what you're doing and don't lose track of your results and which points go with which intersections and which arcs go with which lines and all that stuff. So just need to pay attention and focus on what you're doing, make sure you get a nice accurate construction. But what we should see is that the angle measures stay the same and the side lengths all look about half as big as the original. So based on the example, we know that each line segment is going to be half of the original. If the perimeter started as 15.8, then 15.8 divided by 2 would lead to a new perimeter of 7.9. And then the ratio of the line segments that could represent the scale factor of 1/2, again, we do image length divided by pre-image length. So we have a lot of different options of which segments we could use, actual side lengths of the two triangles, or we could use the segments that connect our center of dilation to pre-image point and the center of dilation to the image point. And the angle measures, did the angle measures change? Are they half as big? No, the angle measures stay the same. Angle measures stay the same. So, in summary, when we are constructing dilations, side lengths are multiplied by the scale factor. The scale factor is also sometimes called the constant of dilation. The angle measures remain the same, and a dilation is not a rigid motion because the size changes. If you remember back in Unit 2, rigid motions, the rotation, translation, and reflection, those are called rigid motions because they preserve distance. A dilation does not preserve distance unless the scale factor is 1. And whenever we write the scale factor, we always do the image length divided by the pre-image length. Always image divided by pre-image. New length divided by original length will give us the scale factor. It'll tell us how many times larger our shape become, or it'll give us the fraction, decimal, or ratio for how our shape got smaller. All right, wonderful, well job. Time to go off and practice on your own. We kept it all under 20 minutes, which is half a period if we were doing it live. So good luck, talk to you soon, stay safe.